Hi there, I'm Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm the robot doctor. Here's a video of one of my robots flying around. It can move around obstacles, such as myself, without running into them, because it knows its position and the position of the obstacles on the map. So how does it get its position? It can't use GPS when it's indoors, so how does it know where it's at? A robot needs to be able to measure distances to nearby landmarks on the map and use what we call localization to answer the question, where am I? We'll explore that in Lesson 104. And we can do that with the math you may already know: geometry, trigonometry, algebra, and a few concepts from physics. Now there is a good bit of math in this episode, so get your pencils ready. So what do we mean when we say localization? One thing the robot needs to do its job is to know where it is on the map. Localization is finding that position on the map. It literally means the process of getting located. Hey robot, where are we? Robots can localize using their internal systems and sensors, or they can use external systems such as GPS. In either case, the general approach is very similar. So let's look at an example problem.
Imagine your robot is in a yard with a tree, a bush, and a bench. These three items are marked on the map the robot has. The robot also has a sensor that can detect each of the three objects and tell the robot the distance to each. Before we get into the actual math, how could we use this information to figure out where our robot is located? If we have a range to a tree, we know we are somewhere around that tree. For example, imagine we know we are 10 meters from a tree, but we could be 10 meters to the north of the tree, or 10 meters to the west, or maybe the southeast, or 10 meters in any other direction from the tree. We can see that this forms a circle with a radius of 10 meters centered on the tree. From that, we have narrowed down our robot's possible positions from being anywhere in the yard to being somewhere on this circle.
Now, let's combine our knowledge about the tree with our knowledge of the other objects in the yard.
We also know our robot is on a circle centered around the bush as well. These two circles must touch somewhere, since our robot can't be in two places at once. If they just barely touch in one spot, there is exactly one point where our robot can be, and our problem is solved. However, in most situations, the two circles will intersect in two places. How can we figure out which one of the two intersections is the correct location? Well, for that, we need a third reference point. In this case, we can use the bench. Now, with three circles, they all intersect at only one point. This is how a robot determines its location in the yard.
And fundamentally, this is how the GPS in your phone gets your location, using satellites above you. So the general flow is detect at least 3 landmarks whose position is known on the map, determine the range to each of these landmarks, calculate where these range circles intersect. This intersection point is the robot's position. Now, let's calculate how to find that position. If we recall from geometry, the formula for a circle is x minus a quantity squared plus y minus b quantity squared equals r squared, where ab is the coordinate of the center of the circle, and r is the radius. Let's go back to looking at the tree. We know we are 10 meters from the tree. From our map, we know the tree is located at 2, 13. So if we just consider the tree, we have the equation x minus 2 quantity squared plus y minus 13 quantity squared equals 10 squared. As we said earlier, if we only look at one object, then we could be anywhere on the circle. So let's add one of the other objects to help narrow down the possibilities. In our example map, we will use the bush as our second object. It is at 13, 11, and we know we are 5 meters from the bush. We can use the equation of the circle, that's x minus a quantity squared plus y minus b quantity squared equals r squared, with the location of the bush to get the new equation. X minus 13 quantity squared plus y minus 11 quantity squared equals 5 squared. Now we have two equations, one for the tree and one for the bush. We also have two unknowns, x and y. Let's expand the tree equation and simplify. We first expand the squared terms and combine like coefficients, then set equal to 0 and simplify. Now, let's do the same for the second equation for the bush. First, expand the squares and combine coefficients. Set equal to 0 and simplify. We now have two equations, one for the circle around the tree and the other for the circle around the bush. We can subtract the bush equation from the tree equation. We first distribute the negative sign and then add like terms together. In this case, the x squared and y squared terms cancel out, and we are left with 22x minus 4y minus 192 equals 0. We can divide everything by 4 and solve for y. And simplify. This now gives us an equation for y in terms of x. We can substitute this back into our original equation to find the possible locations for the robot. Using our equation for the circle around the tree and our new relationship between x and y, we substitute in for y, simplify, and expand the squares. We then group similar terms again and multiply both sides by 4 over 25 to simplify some more. Subtract 16 from both sides to set equal to 0. What we are left with is a quadratic equation. From algebra, we know how to solve quadratic equations. In our case, a equals 5, b equals negative 108, and c equals 580. We substitute our values for a, b, and c, then simplify the equation. Remember that the quadratic equation produces two answers, depending on whether you add the 8 or subtract. In our case, we get x as either 11.6 or 10. We can then substitute both numbers into our combined equation to find the y values. For x equals 10, we get y equals 7. For x equals 11.6, we get y equals 15.8. And that gives us our two answers, 10, 7, and 11.6, 15.8. So we've gone from knowing we were somewhere on the circle to knowing we were at one of 2 points. In other words, if the robot sees two landmarks, it can compute two possible positions it may be in. We need the third landmark to determine which one is the actual robot position. Let's say the third landmark is the bench, located at 10, 0, and the sensor tells us it is 7 meters away. We can simply substitute in both numbers to see which one works. If we substitute in 11.6, 15.8, we would see that we get 252.2, which does not equal 49. Therefore, our robot can't be at that location. Let's try the other possible position. If we use 10, 7, we find that we get 49, just as we wanted. Therefore, that is the robot's actual position. And that's it. That's the math that goes into figuring out where a robot is. And here you can see a robot keeping track of its position, allowing it to maneuver around obstacles that are in its way. In this session, we have discussed how robots calculate their positions using the ranges to some landmarks with known positions on the map. We have walked through how to calculate the intersection point of circles and how to use that information to determine where the robot is. We have successfully localized our robot. Now get your pencils ready for today's challenge questions. This week's challenge question is, if our robot had moved farther along in the yard and it was now 5 meters from the tree, 10 meters from the bush, and 5 meters from the pond, where is it? Again, the tree is at 2, 13 and the range is 5 meters. The bush is at 13, 11 and the range is 10 meters. Finally, the pond is at 5, 22 and the range is 5 meters. What is the robot's position? For our second question, imagine the robot only sees 2 landmarks, a pile of rocks and an umbrella. The rock's at the position 10, 0, and the umbrella is at the position 20, 0. The distance to the rocks is 5 meters, and the distance to the umbrella is also 5 meters. Can you still determine the position of the robot, even though there are only 2 landmarks? Again, you are 5 meters from 2 landmarks, rocks located at 10, 0, and an umbrella located at 20, 0. Can you determine your position with only 2 landmarks? I'm John the Robot Doctor. See you next time. Hey robot, where are we?
You can find these video lessons online at WQED.org/therobotdoctor.